Well, hello, everybody. Welcome to the first of 16 animations, narrated presentations that will cover the 13 chapters. Did I say 16? I meant 13. 13 chapters that we are covering in this semester. And there will be one animation series for each of the 13 chapters. Now, as a consequence of the size of these chapters, those narrations could get quite long. So one of the things that I've realized is that it is better to break these up into smaller chunks. So what you're going to find with each of these narrated presentations is that they are divided up into sections using what I've referred to as concept check questions. And there is a slide inserted in each of these locations where it points out that this is a time for a break. Here's a concept check question. And that question will bracket the break. So at the end of the section, I'll introduce the concept check question. You are more than welcome to take a break. You can close the presentation down. You can pause for a while, walk away and come back, whatever you feel like you need to do at that point. But when you return to look at the next section, you'll get the answer to the concept check question because I'll restate the question and provide the answer at that point. And so, for instance, this presentation is broken up into 3 sections. Probably that is going to be the average, depending on how long the presentation is and how convenient it is to break it at various points along the way. But at each point, there will be a concept check question. And then I usually end every presentation with a final concept check question that serves to summarize the last section of the presentation, because each of these concept check questions relates to the section of the presentation that you've just watched. And it would be a good practice for you to think about these concept check questions because you're going to be answering similar sorts of questions in written form. That's right, written questions on each exam. So you can expect to answer at least 4 written questions on each of the 5 unit questions, the unit exams. And then on the final exam, there are going to be 6 written questions as part of the exam. So it would be good practice for you to think about these concept check questions, perhaps even write an answer before you look at the next section and get my answer to the question. So that gives you a little bit of an overview as to how these presentations are going to work. That being said, then let's get on with this. First one, this is kind of, you could imagine, an introductory chapter because the focus of what we're going to be talking about this semester in all 13 chapters is the relatedness of life forms. And we are going to work our way through the biological classification system by way of looking at the major classifications, and we're going to be looking at the characteristics of each classification. We're going to be looking at their evolutionary origins. We're going to be looking at some very specific representatives of each of the groups to make or to give you a better feel for the diversity of life. But in order to understand that diversity and the unity which we recognize exists amongst life forms, we really do need to discuss in more detail than you've probably discussed previously the theory of evolution and the idea of descent with modification, which is in fact what Darwin and Alfred Russel Wallace's preferred terminology was. Now, you may not have ever heard of Alfred Wallace, which is kind of unfortunate because he kind of gets pushed into the background. And in some sense, Wallace himself was kind of to blame for that. But Darwin always considered Wallace to be a co-discoverer of descent with modification, what we would refer today as evolution and natural selection. And as we talk about this chapter, I'll introduce you to Wallace's role and give you a little bit more information about Wallace. But the modern terminology that we use today for the theory of evolution is not to refer to it as the Darwin theory of evolution. We refer to it as the Darwin-Wallace theory of evolution, because we really do now accept that Wallace played a central role. He came to very much the same conclusions as Darwin did, making very similar observations in a totally different part of the world to Darwin. Read a lot of the background literature that Darwin himself actually read while he was on his journey around the world on the Beagle, that you probably have heard about. And as a consequence of having an opportunity to think while he was recovering from his latest bout of some fever that he'd caught in Southeast Asia, Wallace basically reached the same conclusions that Darwin reached as he examined his specimens that he brought back with him from his voyage. And so we really do have to acknowledge the fact that Wallace is a co-developer or co-discoverer of the theory of evolution. Why Darwin gets greater credit is twofold. Number one is that Wallace himself considered that Darwin had primacy, even though, as you'll see, Wallace probably ought to have been given primacy on the basis of how one of his manuscripts was handled, and there's a whole story there. But number two, Wallace himself actually gave Darwin the greater credit. And the reason is because a year after Wallace and Darwin's ideas were first made public, Darwin published On the Origin of Species in 1859. And in that book, Darwin not only lays out the case for evolution and natural selection or descent with modification, but also provides a huge body of evidence based on his observations, both of his specimens and things that he knew. And you really need to recognize that Darwin was probably the most famous biologist / naturalist of his day, certainly in the English-speaking world, if not worldwide. And this is the reason why Wallace had already been in communication with Darwin about other things that he had been observing, and why, when it came time to submit his manuscript on descent with modification, he thought of Darwin first. And that would start a whole series of events, which we'll get into. But we also need to recognize that both Darwin and Wallace did not operate in a vacuum. They really did build on work that had gone before. And one of the things that most people don't realize is that the whole notion of evolution, the fact that life forms change, is a very, very old concept. We can trace that back approximately 3,500 years is where we find the first written record of what we would refer to as an evolutionary concept, or a concept of evolution, written by the Greek philosopher Anaximander. And we know that throughout these intervening years between Anaximander and Darwin, many people proposed various ideas that we would refer to as a theory of evolution, or at least a concept of evolution. It would not be until just prior to Darwin being born that the most famous biologist of that period, Jean-Baptiste Lamarck, would propose his own evolutionary theory, which would be what we could term today the first coherent theory of evolution, where not only was it proposed that life would evolve, but a mechanism for the evolution of life forms was also proposed. That it was wrong is neither here nor there in terms of the history of evolutionary thinking. And when we talk a little bit more in depth about the nature of Darwin's theory, we'll also address Lamarck's theory to understand why Lamarck was actually wrong. There are some very simple observations that we can make about Lamarck's theory of evolution that clearly indicate that in as much as he was struggling with the idea of organisms evolving and recognized that organisms evolve, his mechanism was wrong, and probably because of a lack of information more than anything else. So one of the things that I always like to do is show a timeline. And so one of the things that I'll do is jump over those first few slides and show you the timeline. So this is a timeline that lays out the individuals who we know had a lot of influence over both Darwin's thinking and Wallace's thinking. So individuals that we know for certain both Darwin and Wallace read were Hutton, Malthus, to some degree Lamarck. We know Darwin read Lyell. In fact, Darwin was a good friend of Lyell and figures in the story, not only because he was the most famous geologist at the time, and probably we could consider him to be the father of modern geology through his 3-volume book, The Principles of Geology, that you can see referenced here. Both Darwin and Wallace were familiar with Cuvier's work, and we'll talk a little bit about Cuvier because he, of all the biologists of this period, was the first to recognize just how significant fossils truly were. Now, of course, you can see Wallace here, and we will get to talking about Wallace's role in all of this as well. But we want to address some of these individuals. I want to talk about Hutton and Lyell because we have to talk about them together. The book does not address Malthus particularly in detail, but I'll give you a little bit of information about Malthus because I've studied him for another class that I used to teach at Valencia, and so I have a lot of information about Malthus. So I'm not going to dig into the details of that, but you do need to understand what Malthus was saying in his document. Some people say it's an essay. I would be more inclined to say that it's a pamphlet because it grew to be about 68 pages long, which is pretty long for an essay. I'll also talk a little bit about Cuvier. I have a little bit of a connection to Cuvier because of some experience or an experience that I was able to have back in 2012, and I will address that here, and you'll hear me talk about that a lot in upcoming presentations as well because it's of significance. So this is our timeline. And so you can see that while Darwin publishes his book in 1859, there's a lot of preceding information that we need to reference as we go, because there's a lot of interesting things to talk about here. So we could begin perhaps talking about a little bit of philosophical background. As I said, the Greek philosophers, and Anaximander is the one who comes to mind first of all, proposed the notion that life was subject to change, that it did evolve. In fact, the Greeks struggled with this question for a while, and they actually proposed a number of ideas that we would recognize today, that life evolved in water, that it eventually transitioned to dry land and rose to dominate land. Those are some ideas that we would agree with wholeheartedly, because we know that life evolved in water, in an aqueous environment. Whether it was an ocean or a shallow sea is subject to a lot of debate, and we'll get into a little bit of that in an upcoming chapter. We'll talk a little bit about the origin of life because we need to. But with the emergence of Plato and his student Aristotle, a different view of life on Earth would emerge. Now, it was not necessarily an anti-evolutionary philosophy, nor was it one of a young Earth philosophy or a natural creation or a divine creation philosophy, but in combination with the thinking of Judeo-Christian scholars who were influenced by Greek philosophy via a number of different routes. We're not entirely sure of all of them, but we know that Plato and Aristotle certainly influenced the thinking of a lot of early Judeo-Christian thinking. And so the combination of the Genesis story and a combination of particularly Aristotelian thought led to the young earth divine creation philosophy known as natural theology that dominated the thinking in Europe from around the early 1500s all the way through into the mid 1800s, almost around the time that Darwin published On the Origin of Species. Now, this is not to say that there were not people who thought otherwise. It's not to say that there were not people who thought that the Earth might be a lot older than this philosophy gave credit to. But the strength of Aristotelian thought and the strength of its combination and its adoption in part or in total as part of the Judeo-Christian philosophy of the origin of life would basically preclude any other thought being widely accepted. And perhaps what had the strongest influence, and you can see the note here, is the notion that Aristotle came up with, that all life forms here on the planet fitted into a ladder, the so-called scala natura, or ladder of life. And that ladder had rungs on it. And each one of those rungs represented an organism, with simple organisms at the bottom of the ladder, more complicated organisms on rungs higher up the ladder. And of course, as you might guess, at the top of the ladder would be humans, considered to be the pinnacle of life on Earth. And it was this observation and its incorporation into the thinking of Judeo-Christian scholars as they were thinking about the Jewish tradition, the Genesis tradition, that would lead to the divine creation, young Earth idea. Now, the notion that the Earth was really young was also not an old idea, but actually a relatively recent idea. It was first proposed in the 1500s as a result of the work of an Irish bishop named Bishop Ussher, who used the genealogies listed in Genesis to try and figure out just how old the Earth was. And he actually assigned a day and an hour in the year 4004 BCE as the actual day of creation. He was very confident that this was the day of creation based on that time, on the genealogies. And so these ideas became firmed up in the thinking and dominated everyone's thinking, but it didn't preclude people from thinking otherwise. And so we don't have to look very far from Darwin to see people thinking that perhaps that philosophy might not be accurate, that there might be another way of looking at the origin of life on Earth. Darwin's grandfather, for instance, Erasmus Darwin, proposed his own quote unquote theory of evolution. It was nowhere near as complete as Lamarck's, and it certainly was not as complete as Darwin's. But he nonetheless accepted the idea that life was probably, an organism probably was able to change over time and was subject to change over time. But it would take Darwin and Wallace and their ideas, specifically being able to propose an actual engine that drove evolution and an engine that could be observed that would drive evolution. that would change people's thinking. And the story of where that their ideas came from is not a simple one. It didn't just occur to them suddenly overnight. It was the result of reading a lot of background information. It was the result of making many, many observations. Most of you are familiar with the fact that Darwin went on a 5-year voyage around the world at the courtesy of the British Navy, serving as the naturalist on the voyage and also the intellectual companion of the captain of the ship, so that he had someone to talk to that held similar interests. Ironically, the captain of the Beagle would turn out to be one of the most vehement anti-Darwin campaigners once Darwin proposed his theory when he finally published On the Origin of Species, that you could imagine. And to say that Darwin and the captain did not see eye to eye on the voyage would be a pretty fair estimation, because even Darwin felt that the captain's philosophical position was a little bit extreme. That being said, Darwin still had opportunities to discuss with the captain some of the things that he was reading, some of the things that he was seeing. So this would give him an opportunity to think about some of the things he was reading, but none of this would have an impact. One of the myths about Darwin's voyage on Beagle was that it was the observations that he made that changed his thinking, and or at least started him thinking. But nothing could be further from the truth. Darwin had not even begun to think in terms of life being capable of evolving. It had not even entered into his thought patterns until he started examining all his specimens after he got back. That was when he really started to question what his specimens were showing him and what they were saying about the rigidity of life forms versus their ability to change over time. And it would be a while. He started his investigations of his specimens in 1836, not 1936. And we know that it was not until 1844 that he penned one of the very earliest manuscripts that laid out his argument for evolution and descent with modification. In the case of Wallace, Wallace's background is a little bit harder to pin down, in part because Wallace didn't leave behind as many writings or as detailed writings. He did write a book of his own after Darwin died about evolution and natural selection. Wallace outlived Darwin by many years, by about 30 years, in fact. And he was a constant proponent of Darwin's and went on lecture tours around the world, supporting Darwin's ideas and promoting Darwin's ideas. But did eventually write his own book about evolution and natural selection, as it was starting to be called at that point. But in terms of his background, in terms of his observations and things like that, it's a little bit harder to pin down exactly when he started to think along the lines of evolution and natural selection. What we do know is that he spent a lot of time collecting specimens around the world. That was how he made his living. He spent a lot of time in the Amazon collecting specimens that he carefully boxed up into large chests and put on a ship. Unfortunately, the ship caught on fire and all his specimens were lost. So he lost everything. He lost his source of income. So he spent some time back in England trying to figure out what to do next. Eventually was able to get a little bit of support that allowed him to go to Indonesia and the Indonesian archipelago and the Malay Peninsula, what is now Malaysia and Indonesia. And it was in moving from island to island within the archipelago that he started to notice that there were differences in organisms along the archipelago. And eventually he reached a point where there was a very clear cutoff between the organisms that had obviously been derived from organisms on the Asian continent, in Southeast Asia, and organisms that were clearly derived from organisms that lived in the Pacific Basin, came up from Australasia and New Guinea, up the archipelago from the other direction. And today we refer to what is known as the Wallace line. This is the line, quote unquote, in the sand that delineates where the organisms migrating down the archipelago stopped because they were prevented from going any further because of the, I believe it's the Sunda Strait that separates one of the two islands, or separates two of the islands in the Indonesian archipelago. Anyway, the Wallace line lies there between two of the islands, and the organisms coming down from Southeast Asia were prevented from migrating through because of the body of water that they would have to cross. In the meantime, organisms had been migrating up the archipelago from the other end, and again, they were blocked by this body of water. This is the Wallace line. And as Wallace started to think about why there was this difference between the organisms, why they could only go so far, why they had migrated from where they were, he started to notice that there were significant differences as well. That while it was quite clear as to where they had come from, they were not in fact identical to the organisms that they were clearly derived from. And while he was continuing to collect specimens, he was not really able to put all the pieces together. But at one point, he was forced to take a break from collecting specimens because he caught yet another fever. We know over the course of his lifetime, he had about 7 or 8 different types of fever. We think this time he had dengue fever, which is fairly common in Southeast Asia. And he was kind of fortunate not to die from it. But as he was recovering from this, while he was in his fevered state, apparently, according to his writings, it came to him as to what was the solution. That organisms change, and that the driving force behind the change was that not all individuals are identical, and that some individuals are going to have advantages over others, what would become the basis for natural selection. So why did both Darwin and Wallace arrive independently at these two ideas? Darwin in 1844, Wallace somewhere around, we think, 1854 or 1855, somewhere in there, because it took him a little while to put his manuscript together. And we know from Darwin's public statements that he received the manuscript in 1858, and it would obviously have to come by ship from Indonesia, which would take a little while. There is a discussion now amongst historians as to exactly when Darwin might have received the manuscript. There's a suggestion, there's an inkling that Darwin may have actually sat on Wallace's manuscript for a number of months, that in fact he received it a lot earlier than he indicated. I've been listening to some science podcasts, and one of the podcasts they were actually talking about this. And there is a suggestion from independent sources from the day that perhaps Darwin received Wallace's manuscript at least a couple of months earlier than he indicated. Exactly what he was doing during that time, we don't know. But of course, the cynical might argue that Darwin was finishing writing a manuscript of his own that basically laid out his own thoughts. What we do know is that when Darwin received Wallace's manuscript, he realized that he had competition, because he recognized that Wallace was stating in his manuscript exactly what he himself had been quietly saying to others, had quietly written in a manuscript, but had not had the nerve to publish, because he was very nervous about the reaction that people would have to his ideas. He basically sat on them for about 15 years until Wallace's manuscript prompted him to do something about it. What did he do? He talked to Lyell and Joseph Hooker, who were important members of the Royal Society. Wallace had asked Darwin to read his manuscript to the Royal Society, and Wallace felt that with Darwin reading it, it might give his manuscript a little bit more weight because of Darwin's fame as a naturalist. Darwin recognized that he could do this and should do this, but he also recognized that this would take away his primacy, because the person who publishes first gets primacy. So he asked Hooker and Lyell what to do. Hooker said, give me the two papers, your manuscript and Wallace's manuscript, and what I will do is at the next meeting, I'll read the two manuscripts back to back. As it turned out, there were only about 30 people at the meeting. It was a bit of a ho-hum. No one really paid a whole lot of attention to it, and the meeting passed very quietly. It wasn't until Darwin released On the Origin of Species a year later that the controversy hit, and people started to question evolution and natural selection. And there was a lot of resistance and pushback. But Darwin's book was so popularly received that in the first year of publication, it went through 3 editions. By the time it got to the 6th edition, 2 years later, it was one of the most widely read books, at least science books, of its day. And today, we know that On the Origin of Species has only been outsold by one other book, and that's the Bible. Of all books published in the English language, On the Origin of Species is the second most published of English language books. And it is a very excellent book to read. If you want to read a really well-written book on the nature of evolution and natural selection, you can't really beat Darwin's book. Now, it's a bit tough to read because it's written in a version of English that we would not be comfortable with. It's not a modern form of English. It is written in the English of its day, but it is nonetheless still relatively easy to read and easy to understand. And if you've never read it, I would strongly recommend that you read it, particularly if you have an interest in really coming to terms with what Darwin said about evolution, because he lays it out very clearly in there. The first 6 chapters are about the concept, and then the remaining chapters, so about 3/4 of the book in total, basically provides the evidence that Darwin had accumulated to support his idea. So that gives you a little bit of a background as to how the concept of evolution and natural selection eventually were made public. Let's talk about some of the individuals, however, who really influenced their thinking. So the first individual that's mentioned on the timeline that we need to talk about is Carol Linnaeus. So Carolus Linnaeus is actually the Latinized version of his name, and it's what he is normally known as. He was actually a medical doctor, a Swedish medical doctor, who decided that some attempt ought to be made to try and sort through all of the disparate organisms that had been identified by science at the time and had been described or identified, and try and bring order to what was very rapidly becoming a chaotic system. So Linnaeus organized all organisms into animals and not animals, basically animals and plants. And we still see some leftovers of Linnaeus's work to this day, because if you go and take a botany class, what you'll find is that in that botany class, you're going to cover fungi. Now, in the modern taxonomic schemes, we recognize that fungi are a separate group of organisms in their own right, and we'll talk about them as a separate group of organisms when we cover chapter 31. That's our chapter on fungi. But botanists still cover fungi because Linnaeus labeled fungi as plants, and for a long time, people considered fungi to be non-photosynthetic plants. And there is still, sometimes you'll hear that said, that, oh, I didn't realize fungi were organisms on their own. I thought they were just members of plants. I heard that just recently. Just quietly, I heard someone say that just recently. So Linnaeus created this system. And if you've ever encountered the binomial naming system, if you've ever encountered the taxonomic scheme that begins with kingdoms and goes all the way down to the species epithet, that is basically Linnaeus's system. He developed that, and we still use that to today. We do use it in a different fashion to Linnaeus, but nonetheless, we still use it. And it was Linnaeus's taxonomic system that would be central in Darwin's thinking about the relatedness between organisms, because Linnaeus based his identifications or his connections between organisms on the basis of morphology and anatomy, what they look like on the inside and what they look like on the outside. Morphology is outside, anatomy is inside. And that's how we grouped organisms together. What Darwin recognized is that those groupings also represented relationships on the basis of their origin. And so part of the irony here is that Linnaeus was very much a traditional creationist. He made the statement that God created, Linnaeus organized. A little bit arrogant on his part, but that was what he said. Darwin took this organization of life and said, those connections that Linnaeus talked about, those similarities that Linnaeus identified to create his groupings, exist because of evolution and natural selection. And the tree diagrams that we are so familiar with today that begin with Darwin. There is a famous page in one of Darwin's notebooks where he starts to tentatively draw a small tree diagram. There are no labels on it, but he's just drawing it. This is his first thinking about a tree diagram. And he just puts two words above it. I think, question mark. Very famous page in one of his notebooks. And I believe there's a picture of it. I don't have my textbook in front of me, but I believe there's a picture of this in the textbook. But nonetheless, it was Linnaeus's taxonomic system that Darwin was working with. Then the next person that I've got listed here is Georges Cuvier, or Baron Cuvier, as he is more correctly known. Now, my connection to Cuvier is that back in 2012, I was granted a sabbatical by the college, and I was allowed to take the fall semester off. And I chose to travel around the world. I spent 4.5 months traveling around the world, visiting different locations that were either of importance to me personally or important because of their connection to biology in the classes that I teach here at Valencia. And so when I got to Paris, I really wanted to learn a little bit more about Cuvier if possible. And I knew that there was an exhibition of Cuvier's work at the Natural History Museum in Paris. So when I got there, I found that they were actually celebrating Cuvier's birth. And they had a separate exhibition in an outlying building associated with the museum. So I had a chance to wander through there, see a lot of Cuvier's manuscripts, to see some of the fossils that he collected that they had pulled out of their bigger collection to highlight. Unfortunately, my schoolboy French did not allow me to really read in detail what they were saying there, but I could pick up enough to realize just how significant the work was. And to realize that my understanding of Cuvier's work was a little bit simplistic, because Cuvier not only was studying the fossils of the Paris Basin, he was working with a geologist colleague of his to understand the geological history of the basin. And they did some very, very detailed mapping of the geological history of the Paris Basin. But it was in doing this that Cuvier finally was able to pin down what the significance of fossils really is. Fossils had been known for a long time. The first fossils that we have recorded as being identified actually goes back to the 1600s. The first dinosaur fossil, that of an iguanodon, a type of plant-eating dinosaur called an iguanodon, comes from the 1700s in Britain, in England. But Cuvier recognized that fossils are remnants of organisms that have lived before, that these represent the remains of organisms that have lived in the past. And what he and his geologist colleague recognized was that in the Paris Basin, life had not gone on unchanged, meaning it hadn't been a consistent environment. There had been periodic floods. The Paris Basin is actually the same river, which is the river that runs through the Paris Basin, is actually subject to periodic major flooding. And these are catastrophic floods that not only cover the land, but wipe out many of the life forms that are left there or that were living there. And Cuvier realized that the fossils were the remnants of the organisms that had been killed off by these floods. And he created the term catastrophism to identify this idea that periodically there are catastrophes that can wipe out all living life forms in a particular location. But that doesn't mean that the area remains uncolonized by life, because very quickly, shortly thereafter, new life forms appear. And this he also recognized was being documented in the fossil record, because he could see layers of sediment. And you can see here a diagram taken from the textbook. There were layers of sediments, and he could see in these layers of sediments, as he and his geologist friend were digging down through the sediment, that different layers represented different geological activities. So there were layers that were clearly sedimentary deposits laid down by these periodic floods. But in between those, there were deposits that were laid down in other ways, and it was those deposits that contained the new life forms. So you would see that the sedimentary layer that was laid down by the flood marked the end of all the life forms at that time period. There was the catastrophe. Then the next layer of sediment above that would be full of fossils. These would be the new organisms occupying the region. And then there'd be another catastrophe, and those life forms would disappear. And then you'd have another layer of sediment. So you would have these layers of sediment built up by the alternating flood periods and non-flood periods. What Cuvier failed to recognize, and we're not entirely sure why he failed to recognize this, is that the organisms that were present in each fossil layer were actually related to each other. He didn't realize that the organisms in the layer of sediment that lay above the flood layer were actually there because they were the survivors of the flood. He figured that they were there because they migrated in after the flood receded and recolonized the land. He did not recognize that, in fact, not every organism was wiped out, and that anyone who survived the flood would be able to recolonize the land again very quickly. But he was the first person to recognize just how significant fossils are. And so fossils, we now know, give us the story of life on Earth. But Cuvier was the first to recognize this, but also to recognize that there were periods of extinction. He called them catastrophes and proposed the concept of catastrophism. We would say now that those catastrophes were extinction events, some small, some major, but they were extinction events nonetheless. Then in terms of thinking about the actual processes of geological change, there are two people that we really need to talk about here. The first is James Hutton. Now, Hutton was a little bit of a everyman in that he was a farmer, he was a shop owner, he did lots of different things over the course of his life. But it was his observations of the environment around him, particularly along the east coast of Scotland, where his family sheep farm was located, that would lead him to start thinking about how the Earth's surface changed over time. So the next picture that I'm going to show you on the next slide is important, because this is one of the first features that Hutton looked at that made him realize that the common explanation of the origin of the Earth's, particularly in terms of its geology, simply could not be correct. This is what is known as a Hutton discontinuity. And what's important here is to recognize, and I'm going to fire up my drawing tablet and pen, which I have with me on the desk here so I can make notations on the slides. What is important to note is this line that runs through here, which is it should be pretty obvious to you. And you can see that the layers of sediment in this layer are vertical, whereas the layers here are horizontal. Now, the dogma about these geological layers and these sedimentary layers in Hutton's time were that these were all laid down by the Noah flood in Genesis. But the problem with this is that if that was in fact their origin, they should all have been laid down vertically. Sorry, horizontally, not vertically. So why do you have this vertically oriented layer of sediments overlaid by a horizontal layer of sediments? That suggests that there must be different types of geological activities taking place that's reoriented these vertical sedimentary layers to turn them into vertical layers from what must have obviously been at some point horizontal layers. But then how did they get laid over by subsequent horizontal layers? It suggests that these layers must be laid down by a flooding event that occurred after these layers had been laid down, but then had also been turned vertically, because it would be almost impossible to imagine some process that could leave these in a horizontal orientation and turn these underlying layers into a vertical orientation without disrupting the horizontal layers. And so Hutton started to realize that the Earth must be more dynamic than it was being given credit for, that there must be some ongoing geological activity that was changing the shape of the Earth and the face of the Earth. So the question then became, what was the nature of those activities and how did they operate? Well, he could see weathering. That was very obvious. And there was weathering by airborne particles and water. And there was some evidence of geological activity in the form of earthquakes and shifting of the land in response to earthquakes and those sorts of things. The significance of those were not fully understood. their effect on reshaping the Earth was not understood. The whole question of plate tectonics and movement of continents was obviously not understood. That's very much a 20th century concept and very much a mid-20th century concept, 1950s and 1960s. And 1970s was when the plate tectonic theory was firmed up. But Hutton realized that these geological processes must be more significant than people were giving them credit for. And what he also recognized, because some of the large geological features around the world, most notably the Grand Canyon in Colorado and Arizona, was starting to be explored, and the layers there were starting to be recognized as being quite significant. And the recognition was that the river itself must have been responsible for carving out the canyon, because you could see the process taking place every time the river flooded in the spring. You could see that large amounts of sediment were being carried down, and that sediment obviously represents rocks and soil being removed by the rapidly moving water. What Hutton said was that you didn't need rapid changes over short periods of time, like the flood of Noah, to create large geological change. You could actually get large geological changes using less drastic, less dramatic geological events, so long as they took place over long periods of time and did so more or less at a uniform rate. And he created an idea or a concept called uniformitarianism, which meant in its simplest form, that the geological activity that you see today is the same geological activity that took place in the past, and the rate at which you see it taking place today is the rate at which it has taken place in the past and for as long as it's been taking place. In other words, geological processes are uniform. They may not be dramatic, they may not be drastic, they may not cause rapid changes, but while they may only be making small changes over the course of a person's lifetime, because they are operating over long periods of time at this uniform rate, they can create very large changes. It just requires more time or sufficient time. And so Hutton was actually one of the first people to really start thinking in terms of the Earth being significantly older than people were willing to give credit for. There were individuals who were already starting to think, well, the Earth can't be just 6,000 years old. It's got to be older than that. But what really stymied a lot of that thinking was an English chemist by the name of Lord Kelvin. Now, if you've heard of the Kelvin temperature scale, that's where this comes from. And Kelvin, as a chemist, had a lot of sway because he was a very famous, very clever chemist. And he calculated what he thought was the age of the Earth. And he said the Earth could be no older than 1 million years. That was the oldest that he was willing to, oldest age he was willing to give to the Earth. And because of his influence, that became the fixed age of the Earth if you wanted to consider a quote unquote old Earth versus a young Earth. And it would take many years for people to overcome the influence of Kelvin and be able to propose a significantly older age of the Earth. It would take into the 1940s for people to get really comfortable with the idea of the Earth being billions of years old. It would take a lot of investigation and observation and the recognition that the inside of the Earth is still very much hot and molten to start people thinking that perhaps the Earth really was billions of years old. And once it was recognized what the energy force was that was driving the sun, nuclear fusion, and that the sun itself was about 4.5 billion years old, and that was the age of the solar system, well, then the Earth really ought to be about the same age as the rest of the solar system, the age of the sun, about 4.5 billion years old. But that would not, that thinking would not emerge until around the 1940s, 1950s, and would actually start to give impetus to the notion of continental drift and plate tectonics, even though the idea had been proposed many years before. So Hutton's got this idea of uniformitarianism, and it starts people really thinking, well, maybe the Earth it really ought to be considered to be older than 6,000 years, because how else could you explain these inconsistencies, these discontinuities? And Hutton himself would identify 4 or 5 of these, and people who heard about Hutton's work would themselves find more discontinuities. One of the most famous discontinuities actually was discovered in the European Alps. It turns out that the European Alps themselves are a upthrust of ocean floor as a consequence of Africa pushing against the underside of Europe. And there is a major discontinuity where this upthrust has occurred. That gave rise to the Alps. So the other person who is central to the geological thinking as far as Darwin and Wallace are concerned is Charles Lyell. And I've already indicated that he was the most famous geologist of his time. And he wrote a 3-volume work, Principles of Geology, that formed the foundation of modern geology as we know it today. We know that Darwin took the first volume of the book with him on the voyage of the Beagle and read it. And in that volume, Lyell lays out an extension of Hutton's uniformitarianism, which is referred to, Hutton's gradualism. I keep getting these two ideas confused. So scratch uniformitarianism from the previous and substitute gradualism. Hutton was gradualism, gradual changes over long periods of time. Lyell is the one who turns it into a uniform process. So Hutton says that large changes can take place so long as the processes that cause them occur over long periods of time, forming gradual changes that accumulate to large changes. Lyell simply says those forces that are in operation causing those changes today were the forces that were in operation in the past and were doing so at pretty much the same rate. And so together, Lyell and Hutton really changed people's attitude towards the age of the Earth, because if you're going to have these geological processes occurring, if they're going to take long periods of time, if they're going to be gradual, then you need time. You just need time. And you can't have a young Earth and have enough time for these processes to occur. And because you can observe the processes in action, there obviously has to be a case for the Earth being substantially older than the young Earth model would give credence to. So Darwin's already absorbing these ideas as he goes on his voyage. We know that Wallace absorbed these ideas as well in some of his readings throughout his spare time in his collecting. Now, there is one other person who is not talked about in detail in the book, but is on the timeline. So let me flip back to the timeline for a minute. And you can see him turning up here, Thomas Malthus. Now, Malthus is not a scientist. He's the odd man out here, in that Malthus was an economist. And Malthus wrote this essay, an essay on the principle of population, trying to establish the principles that would limit population growth. Now, he was not talking about organisms in general. He was focusing as an economist on what would limit the growth of human populations. And what he recognized was that resources were going to be the single most significant limiting factor on human populations. Because if the population increased without check, it would very quickly outgrow the ability of the resources to supply it. And there's a whole series of economic principles in play here that I don't want to get into. But the basic idea here is that as populations increase in size and resources don't increase at the same rate as the population increases, there's going to be a conflict over those resources. There's going to be competition for those resources. And as soon as you introduce the notion of competition, you introduce the idea of winners and losers. Now, in Malthus's philosophy, the winners were going to be the people with resources, and the losers were going to be the people without resources. But Malthus also recognized that if you were a person with resources, you were probably more, or at least this was his philosophy. Malthus stated, I shouldn't say he recognized, Malthus stated, and in his philosophy, I guess you could say he recognized, that people with wealth would be more well-behaved than people without wealth. At least that was his idea. And he laid this out pretty succinctly in his pamphlets. And he said that people with wealth would limit their reproduction, whereas people without wealth would not. And this was based on his observations. Obviously, we would not agree with that. He was very much, however, a man of his time period, and this was a very popular idea. What he then recognized, and this he did truly recognize from observation, is that not only would this competition for resources limit human populations, but it would set up situations where you could promote other check factors on population growth. So some of the other checking factors on population growth that Malthus proposed were war, because of course people get killed. And if you think about the people who get involved in wars, it's the young males, and certainly in Malthus' time, that was certainly the situation. And that would result in the loss of the individuals who were most likely to produce children in their families. And so the loss of those individuals would limit population growth, because it would reduce the opportunity for producing offspring. In parallel with war, you could also think in terms of disease, often promoted or triggered by conflict, and famine, also caused by limited resources, caused by overpopulation, caused by disease. Famine goes along with it. And all of these would be factors that would limit the growth of human populations. And this is what Malthus proposed, that there would not be unlimited growth of human populations. Now, what he also talked about was the fact that humans could increase their access to resources through their technology. So through farming technology, through industrial technology, you could create the opportunity for making more resources available. What he failed to recognize was that part of the farming technology is what we would today refer to as artificial selection, where you selectively breed organisms to create the types of organisms that are beneficial and give you the sorts of traits that allow for improved yields in terms of plants, higher crop yields, more meat production, those sorts of things. That in fact you could limit the growth of all organisms by selectively breeding them. You could change the nature of those organisms by selectively breeding them. He came ever so close to almost recognizing that his principles don't apply just to humans, but apply to all organisms, that there are always going to be checks on the growth of populations of all organisms for pretty much the same reasons as he gave for limits on growth of human populations. What Wallace and Darwin did was simply recognize what Malthus failed to recognize, that the sorts of population limiting factors that Malthus was proposing for human populations would work equally well for all organisms in the natural world. It might take time for that to happen. Certainly, these factors would influence populations. And once there's this influence on populations, this limit on growth because of resources, the opportunity for winners and losers, what is the consequence of that for the nature of the organisms that are subject to these influences? And from there, it's not a huge step to the notion of natural selection, the idea of descent with modification. Or as Wallace and Darwin really objected to, survival of the fittest. That was a term that they really, really, really did not want to see used, because they realized that people would misunderstand what that meant. And that is still true to this day. They much preferred the term descent with modification, but they also recognized, because we have all the letters that they wrote backwards and forwards to each other after the publication on the origin of species, because they kept in contact with each other throughout Darwin's life. And Darwin was really good about keeping his correspondence. So we know that they really hated survival of the fittest, that they really wanted descent with modification to be the terminology that would be used, but they also recognized that people would find survival of the fittest much cooler than descent with modification. So they basically resigned themselves to survival of the fittest as being the terminology. So the last person who we need to talk about is not really someone who influenced either Darwin or Wallace in terms of their thinking about natural selection and descent with modification, because that was the one thing that Jean-Baptiste Lamarck really didn't get right. His idea of the evolution of organisms was based on two ideas that you can see spelled out over the next two slides. The first is what is called use and disuse. You either use it or you lose it. And so if you think in terms of any feature that an organism possesses, if that feature is something that organisms continually use, they retain it. It might even get bigger depending on how important it is. But if it was something that they don't use, then eventually it would wither away and disappear. Now, as you'll see as we talk more about evolution, we can talk about an idea that sounds very similar to that. It's not use and disuse, however. It's more in terms of cost-benefit analysis. So our modern understanding of why things get lost over the course of an organism's evolution is not because of disuse, it's because of the cost-benefit analysis. If it costs more to maintain something than the benefit you get from it, then you will lose it. Now that's different from use it or lose it, because something that you have that costs more to retain than the benefit you get from it is not necessarily something that you're not using. It may very well be something that you're using. You're just not getting much benefit from the use, and therefore it's not something that you would want to retain. So an example of that is having a 6th digit on your hand, which happens to be a dominant trait. It just so happens that 5 digits, for some reason which we don't understand, the recessive trait here, is the one that is favored by natural selection. And so even though individuals are born with that 6th digit on their hands or their feet or on both, periodically, about 1 in 400 births, it is not the favored trait. And so it has, by and large, been lost. But because it's a dominant trait, it's still retained within the human gene pool, but not as a very common trait anymore. The vast majority of us are homozygous recessive for 5 digits. But that's the notion of cost benefit. Having that 6th digit is not a benefit. It's actually somewhat of a disadvantage. So even though some individuals still are born with it, by and large, most of us have lost it. Likewise with the appendix. The appendix was actually substantially larger when we were primarily herbivores and relied mostly on plant material. Now that we have switched mostly over to animal-derived protein, we don't need a huge digestive tract to process the plant material. And what is now our appendix is actually a remnant of a larger sac that was used to delay the movement of the plant material through the digestive tract to give more time for it to be digested. But now that we cook our food to soften it, to pre-digest it, because that's what cooking does, and we rely on animal-derived protein a lot, we don't need that extra chamber to process the plant material. So we're eventually eliminating it. We're doing the same thing with our wisdom teeth, because our jaw is getting shorter, and so there's a lack of room for it. So a lot of people are now being born with either missing wisdom teeth or unerupted wisdom teeth. They haven't emerged through the gum line. And so they get removed because there's insufficient room for them. So these are all examples of a cost-benefit analysis. It's not use it or lose it. It's the benefit that you get from it is not equivalent to the cost that you pay for maintaining it. So you lose it. Lamarck said you either use it or you lose it. And that's incorrect. The other was, and this is the one that most people are familiar with, is that any characteristic that an organism accumulates over the course of its lifetime is going to be passed on to its offspring. And that could be any trait. The example that I normally use is the fact that I actually had an appendectomy about 10 years, 12 years before my daughter was born. But my daughter was born with an appendix. I did not pass on my lack of appendix or my appendix scar to my daughter. But if Lamarck was correct, I should have, because that was a trait that I had accumulated over my lifetime. The one that he is really most famous for is the muscles of a blacksmith, where the son of a blacksmith would be born with large muscles because of the large muscles the blacksmith had developed as a consequence of his work. And the one that is a little bit more controversial, because while Lamarck is credited with talking about this, he really did not talk about this very much. He only wrote a couple of sentences on this, and this is the elongation of the giraffe's neck. The argument being that the giraffe's neck got longer because it was trying to feed on leaves at the top of the tree. And by stretching to feed on those leaves, the neck got stretched. And from generation to generation, it got longer and longer. We now know that that's not correct. Giraffes will feed from the tops of trees under certain circumstances, but they prefer the younger, softer leaves that grow around the lower margins of the trees, and they will actually bend down. They're a large antelope, They will actually spread their front legs and bend down in order to be able to get access to those leaves. So what is the purpose for the long neck? Well, it's the reason why many organisms have the traits that they have, particularly the males. It's all about competition for mates. You've probably seen footage of antelopes, particularly the male antelopes, having head-butting fights to get and keep small herds of females. Well, the male giraffes did the same thing. They fight over access to the females, but the way they do it is to swing their heads against each other. And of course, if you've got a long neck, that allows you to build up a lot more momentum before you drive your head against the head of your opponent. And if you look at the top of a giraffe's head, you actually see little nubs that represent the remnants of the horns that other antelopes have. And again, it's all about fighting for mates. But Lamarck is said to have said that these long necks were created as a consequence of stretching for the leaves at the top of trees. No, the neck got elongated because it allows you to use your head as a better weapon against your opponents when you're fighting for access for mates. So it comes down to the age-old story of reproduction. So these are the people that influenced Lamarck and Wallace. And in part, their ideas directed the thinking, or at least influenced the direction of the thinking that both Wallace and Darwin went in. So here's our first concept break. So if you are ready to take a little bit of a break, and I would encourage you to take a break whenever you're ready. You don't have to stop at this point if you don't want to. It is possible to click on an arrow icon at the base of the recording screen to click straight through to the next section. But if you want to pause for a moment, go and get a drink, take a bathroom break, whatever it is that you want to do, feel free to do so. I won't know. I am going to turn off the recording and then turn it back on again to start the next section after I give you the concept check question. So here's the question that I'll answer at the beginning of the next section. How did Hutton's and Lyell's ideas influence the thinking of both Darwin and Wallace about evolution? I'll see you on the other side of the break with the answer.